So we should start. A few more people coming. I was thinking that I should do a joke, and I found exactly the perfect joke. Are you stuck here since yesterday because you couldn't find your way out? Actually, I was here, and on the way out, I was like, okay, did I took a left or a right? And it took me a while to find my way. So I thought about maybe no one will join my talk, or they will be stuck here because they couldn't find their way out, as I did. So welcome. Today, we're here, or I'm here at least, to talk about asynchronous messaging. This has been like the thing that I do in the last 10 years, ever since I found out that there are easier ways of doing microservices intercommunication, pretty much. And back in the days when microservices were a thing, the new shiny thing that everyone wanted, the first go-to option for splitting the monolith in small chunks was to do HTTP requests. That's the usual step to evolve your architecture, right? So since then, I discovered there is another world out there that has different concepts, and it is kind of hard to unlearn what you know from HTTP when you start to embrace asynchronous messaging. So who am I? My name is Irina. I'm a software architect at Particular, and I blog from time to time at Irina Codes. And I also, I'm a DOM-trained author. You can find a course for, on messaging, of course, on mass transit over there. So since we're talking about microservices and this journey around communication, we cannot not mention the monolith, right? This is where we all kind of started. And some of us are still there even today. Okay, so to me, I must admit, as a developer, the life was easy. I mean, you had everything in there, all the dependency, everything, one place. You searched in the code, and you didn't need to worry about what others are doing or what other teams are doing. Where merge conflicts, because you had one single huge source code, but that's it. So I'm gonna admit, I was guilty. I am guilty. I love monoliths. I still love them. They still exist, by the way, in different systems, in different companies. So a monolith is self-contained. We have that single code base, and there is a single deployable unit that makes life easy for developers. All the dependencies are in one single code base. There aren't too many moving parts. And usually this is a single technology stack, right? We all know that the goal is to have polyglot environments. Maybe just in case we would want to switch a specific component to, I don't know, Rust or Go or Python, we would have that flexibility. In real life, actually, I have never seen it. So if you have a tech stack that is .NET, you most likely would have every single component in .NET. I mean, I haven't seen this transition. So with the monoliths, we have all or nothing deploys. We have green-blue deploys, but you take the chunk, you move it in production, and you hope that it works, right? We kind of have downtimes, or if we do not want to have downtimes, we have to intervene with different systems in between. Almost zero continuous delivery, yeah. Since the code is so big, when you do many changes, you have to also test those changes. So it's hard to test, right? But when it comes about scaling, it is possible. You can give a bigger machine, you can give RAM and CPU power, we can scale it up. But giving more resources to a machine doesn't necessarily would increase in terms of costs proportionally, right? Of course, we could add many instances of the same application, but we would have to put load balancers in between, and we would create things more complicated. Well, so we heard about microservices architectures. What is a microservice? How big is it? Nobody knows. Every company has its own definition about what a microservice is. And we kind of understood this term how we wanted it. So It has its own database, a microservice, right? It is easy to deploy, it is a standalone thing, and it is easy to maintain. Also, they promote it as being easy to maintain, right? Because it's isolated. But is it that easy to maintain? When you chunk your monolith into smaller pieces that start to move around, is it so easy to maintain? As easy as it was with the monolith? I don't think so, right? Because we have so many moving parts now. We get complexity, more complexity that we would want, because we have more moving parts. And unfortunately, these moving parts cause cascading effects in case of failures, right? Because we depend on different other subsystems in our app. We need to monitor them closely. And monitoring is a thing that we kind of do from the moment when we actually need it. Nobody thinks about, oh, we should add monitoring in our system. When the things get hard, we think, okay, from now on, we're going to add monitoring so we can prevent failures in the future, right? So as soon as you start chunking the monolith and separate the components, we will start to realize that independent units are not so independent anymore. And we end up with things like this, big ball of mud, of big ball of HTTP calls, at least at first, right? And we end up with things like this that do different things, or different things like this. Independent, right? With their own databases, easy to deploy. Teams own their own microservice and so on, right? Because we thought that if others do it, for example, Amazon calls sometimes 150 APIs to build a single page. They can do it, right? Usually the tech giants dictate what we want to do with our software, right? Or Netflix that services 5 billion requests a day, and from all these, 97.7 are internals, so downstream APIs, right? They can do it. Why can't we, right? So we do HTTP calls. An HTTP call to another API is super simple. We do a request, we get a response, and we're happy most of the times. Or this is the, let's say, the default scenario that we have in mind when we code things, right? But how do we proceed if things are not so good anymore and our response doesn't come back in timely manner? We're sad then, but we also cause cascading failures inside other components that need this. So what do we do then? Well, we manually intervene and we introduce retrying policies, right? So in case next time, maybe, things can be solved by themselves, right? Well, sometimes it's not enough, because API 2 won't even know what was the content of the request, right? We retry, but from the API 2 perspective, the API doesn't know what was the content, right? So we lose data. And from HTTP, synchronous calls, we start to move on and say, oh, I'm going to do it async. It's faster. We serve the request faster. But in fact, it's still HTTP. It's still async. It's async for us in C#, because we use that syntactic sugar and stuff, and we have threading and stuff. But in the end, the protocol that we use is the same. HTTP, by its nature, is synchronous, no matter how much we're trying to lie. No, it's synchronous because this is the way it was built. So it might look like we're distributing the load because we're doing requests, and those responses may come back, but we actually have the same issues. This appearance of serving more requests is just that, an appearance. It doesn't happen. The server you're hosting but the API on is the same. The problems you're facing are the same. About HTTP, TCP connection for each request, we have absolutely no retries out of the box. We have to use libraries, we have to think about different policies that will save our request. What happens if, I don't know, an API doesn't respond in 3 seconds? Should we retry? Should we cancel? Is that a timeout, right? What status code and what exception do we handle? So we have to think about all these aspects. Another thing is that HTTP doesn't have any delivery guarantees. You do the request, but there is nothing guaranteeing you that the request will be received, so you'll receive a response back. Yeah, there is that happy case where you do a request, you get the response back, and that's it. But in other cases, there's nothing guaranteeing you that the request ends up being on the server side where it should be. Another thing is location transparency. You have to manage every single endpoint that you are calling. You have to discover those endpoints somehow. Either manually, you're coding them somewhere, app settings, in production environments and stuff, environment variables, right? But you know exactly from where to where you're doing the requests. Yeah, so you have some extra thing to manage. But HTTP is super good for public-facing APIs. If you want to expose your API to the outside world, usually REST will be the de facto standard, right? Or JSON over HTTP, pretty much. We're familiar with this. We have been using HTTP since the internet appeared, right? And it is easy to debug because we're so familiar with it. But do we ever think about these stuff? Non-functional requirements, like availability, fault tolerance, latency, throughput, reliability, observability, resiliency, scalability, interoperability, recoverability, and you name it, pretty much everything that ends in -ity, it's something that we might want in our system, right? And I'm going to ask you, how many of these you're having in your systems? Like checkbox, I have fault tolerance. I have availability 99.99%. My system is resilient. It is able to self-recover. Do we? No, we do not even think about all these things if they're not explicitly mentioned in the feature that we have to implement, right? There might be some cases when, I don't know, the business analyst or the team manager comes and say, hey, I need this to be up 99.99% of the times, right? And then you start to think, okay, how do I achieve this? What do I implement? What extra tools do I use, right? How do I ensure that my system is up and running and it is recovering from errors or retrying things? There are many of them. And unless they're explicitly stated, we do not care about them, right? Pretty much we're kind of focused due to the time constraints or I don't know, to what we have in mind. Functionality, features, right? Because those are the things that usually bring us money in return, right? From our customers, from our stakeholders, right? They need those features. And these things are like treated as a second-hand stuff, right? So, for example, in case of e-commerce system that needs to handle a lot of orders during Black Friday, when you explicitly have a thing like this, then you kind of think, well, we have to handle load, we have to scale. But other than that, we do not think about having systems that auto-scale unless we have cloud and that's enabled by default. And we don't think about having systems that are elastic, to be able to handle load when we have peaks and to decrease the number of instances and stuff like that. It's a desiderate, so to say, right? So another thing, how do we handle timeouts? We do a request, we wait for responses, but for how long do we wait? It's who gives us that number? Hey, 30 seconds, 1 minute. And there will be like 1,000 other requests that wait for us, and they will get timeouts. But there is a glitch, something happens in the systems and we're not able to respond, right? How do we handle that? And what happens to all the requests, right? That's a thing that we should have on the back of our minds. Some other things that are very closely related to non-functional requirements or the quality attributes of our system is coupling. Coupling can be of many types, but I'm going to mention two. Temporal. So if service A needs to talk with service B, well, they need to be up and running, able to chit-chat with each other, right? And this is the easiest thing to solve. Another thing is logical. As soon as we start in our code to duplicate things like, hey, this API needs this model, order model, and this other API needs to be aware of that order model somehow, and we start to create another class, and we end up with 10 order models scattered across different components of our system. That's a logical coupling, right? And sometimes we kind of think that, okay, how about we extract, we do some refactoring, right? We're doing HTTP clients that we start to distribute using NuGet packages. The deal with the HTTP clients that we start to distribute because we think it's okay to do so is that they tend to gain weight and they tend to gain business logic. It's one thing to code some information about that, some tests in a package that you distribute, but it's another thing to create spaghetti code just because you introduce some business logic there. And it usually happens, and I've seen it several times. Okay? So duplicating business logic is not a good thing, right? And it's something that we should address. And the road to a good system is not easy. It is sometimes very curved, right? So we kind of agree that we do HTTP calls, and we do REST. And I'm going to ask you how many of you are doing REST APIs? Okay. And now how many of you are really respecting all those 6 guidelines from REST that Roy Fielding going to hide? Right? We kind of choose from REST only those bits that interest us, right? We do not use not even the good verbs. How many of you are using head as a verb? Yeah, I've seen only one hand, right? Head is like a get, but doesn't bring the body back. That's very useful when you rely on custom headers or status codes. Like, hey, check if this item is there or not, right? You don't care about the body, but you do care to see the existence of a specific item. And it has many applicability around industry, right? But REST is simple, widespread. We all know JSON. We do interoperability with JSON or XML. But at the same time, we know that REST has a limitation. We do have tight coupling. As soon as we know the address of that thing that we're trying to call, we have a coupling introduced in our system, right? We know the endpoint, we know the URL that we want to call, and we know where that API lives. That's a coupling issue. Another thing is latency sensitivity. High latency or network disruptions can cause timeouts and, of course, cascading failures. And not only once, I've seen with different themes that we have service A calls B and B calls C, and we have this chain of requests because, I don't know, this is the way we inherited the system, or this is the way it is, and we have to deal with it, right? But if C has a problem, then B will have a problem, and A will have a problem. And that's the cascading failure, right? And another thing with REST is that we get limited communication patterns. Do you know anything about, besides request response? With REST, we do a request, we get a response. The communication pattern involved is request response, right? That's it. There is no other thing. If we do a HTTP request to an API, you have no way of, at the same time, and now doing the same request to the second API or to the third, right? A copy of the same request. It's impossible, right? So we only get this, request, response. With messaging, because this is the thing that I'm trying to preach about, right? What is messaging? Well, messaging tries to give us loosely coupled integration, meaning that as soon as we publish a message or we send the message, or as we would do in HTTP, do a request, that request in messaging transforms itself into the concept of message. that message ends up somewhere in a system, and from there it is picked up or pushed to those components inside our system that care about that, right? So now we do not need to care anymore about who's the consumer of what I'm sending or what's the endpoint that it will reach. We don't care about that, so we have decoupled components. At the same time, because it allows us to store the messages, we would get temporal decoupling, and of course, increased reliability as a consequence. The messages that we're sending won't be lost. And another thing that I think is very important is that the messages can be transformed in transit. What do I mean by this? Is that we can create processing pipelines in which a message go and get some additional information. I don't know, maybe we need to call a specific other endpoint to get some VAT applied on a property, or I don't know, do some funky stuff. We can create pipelines using these messages, and we can add extra information to these messages. One thing that is also important to note is that messaging systems usually trade consistency for availability. What this means is that we get eventual consistency, and we have to shift our mind in such a way to deal with that, okay? Okay, messages have been around since kind of forever. Humans, since the beginning of time, sent messages under different form. I don't know, paper written in and sent out in bottles, or using carrier pigeons. But we kind of use asynchronous messaging from a long time ago, right? And now we equip in the pigeon with more advanced technology. But in the end, the concept was you get something and you send that something asynchronously and not necessarily wait for a response. There will be something reacting to your message being sent. Have you ever called I don't know, a good friend to give a very good news that happened to you? Like you just want to brag about something very nice happened to you, and you call and you call and you call, and there's no one answering. Because, I don't know, that person is busy, right? That didn't end up feeling very well, right? But if you would have left a recorded message and that person would listen, that would give you a sense of relief, right? You got to tell your story right when you wanted to say it, right? So this happens with messaging too. So what is this messaging as a concept? Well, if we were to compare with what we get in REST, in a request we would have headers, a body, payload, and a verb, or an HTTP method, right? When we translate the usual way of doing things with REST to a message, now we get headers that sit on the envelope, and we get the payload that is inside that envelope. And actually, our request gets translated to something like this. Whatever class we want to send is usually C# class that gets serialized. It will be the body of the message. And we would also have some additional metadata on top of it. This metadata is usually similar to the headers that we used to have in HTTP. We can add key value pairs in there. We can have information about who's the sender, where's the destination, and stuff like that. Now, these messages can be of many types. And there are super many types, but these are the most common. We can have documents, like binary encoded string that gets passed around. We can have commands, do something, or process the order, create the invoice, create an order. We can have events. These events are a type of message that are usually more discrete, like order created, account created, and usually state a thing that happened inside the system. And they're usually very small to pass around. We have queries. This is a part of CQRS. And of course, we can have a request reply over messaging too. So there is this paradigm that we can have here. Well, has everyone heard of a queue? Yeah, right? A queue is one of the most important concepts in computer science. We might have learned about it. It's basically a construct where the messages end up, it's first in, first out, just like a queue at the store, right? So the first person at the queue will get its order and will leave. And this is used inside different messaging systems, or wrapped, or we can find them inside different message brokers. So there is a sender application sending a message. That message will end up in the queue, and at the other end of the queue, we'll have a receiver, right? Now, there are different ways of dealing with this. Some messaging systems will make the receiving application pull messages from the queue, and some others will push directly the messages from the queue to that receiver. So there is a nuance, and there is a different performance penalties or not, depending on the model that we have. Now, we talked about HTTP as a protocol, and we know how it functions. But do you ever heard about advanced messaging queuing protocol? Yes. Those of you that have been around for a while and worked with messaging systems, for sure you heard about this. So what's this AMQP? Well, it has the concept of a channel. So I hope I found a good enough representative image. So inside the channel, we have many wires that allow us to pass back and forth information. So it's an open standard protocol for message-oriented middlewares that enables asynchronous messaging between applications, and is popular in event-driven architecture, microservices, and enterprise messaging. So the idea with AMQP is that it's async by nature. It has a guarantee message delivery. It will do no DNS resolve for each message that it gets sent. It has programmatic routing, so it can handle like patterns to route messages to different consumers. It can have retry out of the box. And also a very important thing is it can allow us to acknowledge or not acknowledge out of the box the receival of a message or the message processing. So the idea of AMQP is that it is implemented by message brokers. RabbitMQ, Azure Service Bus supports this. Not all of them support it, right? Some of them are still using HTTP behind the scenes to receive and send messages, but they use queues. About guarantees, we have 3 of them. So the delivery of a message is at most once. So a message will be delivered to a consumer at most once, at least once, and exactly once. And the idea is, depending on this delivery type, we can have slow or fast, the latency is less or more happening. And we get more reliability or less reliability, right? So, for example, for at least once, a message is retried until it is acknowledged. So it will be redelivered to the consumer until that consumer will say, hey, done, I'm done, I processed this. And it will be removed from the queue. Exactly once, messages delivered exactly once, even in failures. So you might lose something in there. But this impacts latency. Well, moving from what we already have to message brokers, these are like control towers. They handle and they know everything that's going on. So they get messages and they know where to send those messages based on what the message contains. Basically, is a kind of database optimized for handling message streams, sort of. In message brokers, one process sends a message to a named queue or a topic. We can have one or many consumers, handles the connections and disconnections, and also it has this concept in asynchronous messaging called dead letter queue. So, for example, if a message cannot be processed for several number of times, it can end up in an error queue, a queue where it won't be lost, right? But we would have the possibility of getting there and moving all the messages in the dead letter queue to the initial queue to be processed. And we introduced basically the concept of recoverability in our system. It has those messaging guarantees because it implements AMQP. It can use also different protocols, and you have here some examples. And if we were to look at where this sits in between our components, we would have a sender application, and that sender application would send the message to the messaging system, where it will be received by the receiving application, or many receiving applications, because we can also have that scenario. So if we were to think about how we handle things in a messaging environment, we are writing things in classes, we are writing header informations, or based on the consumer or the sender, we know where to dispatch that, and we simply send to the message broker. And from now on, the message broker knows what to do with our letter, right? Where to deliver it, what are the constraints, where that message will go in case of the sender not being there or erroring out, and so on. And when it comes about messaging patterns, well, now we have flexibility. We can have point-to-point. Point-to-point messaging pattern is where a sender sends something to a queue, and we know exactly what and where is that queue, and we have one receiver at the end. So we go through that queue to basically send a message. Another thing is publish-subscribe. We have a publisher sending messages to a queue, and from that queue, or in case of RabbitMQ, to an exchange that contains queues, many subscribers are notified. So the difference between publish-subscribe or pub-sub and sending a message and receiving a message is the context where we are at, right? So we have a publisher that sends one single message, but 3 subscribers will receive that message because they receive a copy of that message. So this is fan out, pretty much. And another thing that I want to talk to you about is the request response, but this is done over queues. So a producer will put a message in a queue, a consumer would receive that message, and it will later reply back with whatever we wanted to reply, but in a temporary queue. So we do not have request response as we do in HTTP, but this time we're using this in-betweens, and the road is more complicated pretty much, but we get the reply back. And this could mimic what we have in HTTP APIs, public-facing. So what's in it for us? Why messaging? And I also have a lot of code to show. Well, of course, at first we get increased throughput. So if we have a burst of orders, those orders end up being stored in the message broker. And from there, they get distributed to different consumers interested in consuming order messages. Well, the idea with increased throughput is that we can handle it if we spin up several instances of the same consumer. And this way, we get another design pattern called competing consumers, where the load is distributed because the message brokers know how to send those messages. First to the first consumers, second consumers, and so on. So we distribute the load without us intervening too much, without having load balancer and whatnot, other systems in between. So we get this elasticity. When we know we would have a peak in orders, we can have several consumers, and those will level out the load very easily. So when we come and talk about agility, we get faster development. Once we grasp the concept, the microservices that we develop would be developed faster because we care about what we send and what we consume, and that's it. We care about the contracts that we get, and that's it. Not about integrating or whatever API to make sure that that other API knows what we're sending or what we're expecting and so on. We just send the messages to the message broker, and from now on, there is this other team's job. Okay? So there isn't any tedious processes as before. What we depend is a contract, the part that we want to make sure everyone knows about, because based on that, we can determine what is the message type. So teams will have full ownership and understanding of the code base. And of course, it is agnostic, so we can have consumers that are written in Rust and publishers that are written in C# or Java. Yeah, we get this interoperability out of the box, and we can switch them if needed. Okay, so what do we gain, and what would be the issues that we also gain, right? Because there is no silver bullet in software development. We can process more requests, faster even. We don't lose them, which is a big plus. We have this load leveling, and what do we lose is that we now have another problem, which is eventual consistency. In a system where the orders matter, eventual consistency needs to be solved. And of course, we also get some things. The need of the outbox pattern. Now we cannot have distributed transactions. If we want to save something in a database, but also publish a message, we would need to think about, okay, but we have two different systems, a database and a message broker. Which is first? What happens if I'm saving it in the database, but something happens and the message crashes? It's like, I have an inconsistency, right? So now we have some other design patterns to think about, the outbox patterns or the inbox pattern. And depending on the framework that you're choosing, you might get it out of the box, outbox. Another thing is Saga. So if you want to coordinate processes, Saga pattern is something that you would need. And now you have more complicated things to think about. Another thing is around recoverability. And I'm going to show you some demos around this. So if, let's say, the data contract changed, right? So you published a burst of messages, but you're not able to consume them, or something happened inside your consumer that it errors out. You rely on a specific value or a property that is not there anymore. All those messages end up in an error queue, right? So what you would need to do is to manually dig in there, get each message, fix the problem, and repush them to be reprocessed, because assumingly now your consumer fixed itself or someone did a deploy, right? So there is this recoverability feature that you might have out of the box or not. And it might be easy to solve or not. I've seen a lot of companies doing their own tools that it's more of a DevOps problem pretty much. But if they're using RabbitMQ, for example, as a message broker, they have a plugin that shovels all the messages from one queue to a named queue that you specify. But if you want to edit manually all those 1,000 messages, well, there is some work to do. So I'm going to show you a tool that fixes this. So what tools, frameworks, and systems we have at our disposal? Well, there are plenty of them. Some of them are message brokers, RabbitMQ, ActiveMQ, Kafka is a messaging stream, ZeroMQ, but I do want to talk about mass transit, which is a wrapper around your code that abstracts away your infrastructure, and also in service bus from particular. Yeah, so just to tell you a small story, when I first started with messaging, I used RabbitMQ because that was available back then, but we used their native SDK. And for .NET is that amount of code to send the message, and a similar amount of code to receive a message and to acknowledge that the message is processed and so on. I don't know why, but back then I didn't know that in-service bus exists or that mass transit exists. These two libraries are pretty much like a repository pattern on top of your code that do a lot of things for you. You just configure them and not care about the infrastructure that's behind. And also allow you to switch. Because if you now might use RabbitMQ, but tomorrow you might want to use Azure Service Bus, right? This would make it very easy for you to switch the technology behind. Because the technology behind, yes, it does implement AMQP and whatever other protocols, knows how to handle messages. But in our code, the big pain is when we have to switch and do the code changes that no one wants to do. And what I've seen by being at a particular booth, I heard people saying that, yeah, we kind of have our own wrapper on top of RabbitMQ to make it easier to deal with why should you invest time and people's time doing that when there are already libraries doing that, right? And they're lifesavers. Not only that, but some of them, they have monitoring tools out of the box, as Particular has. So no matter the broker, use a library that abstracts away the infrastructure. For developers, how queue is configured and stuff like that in RabbitMQ shouldn't be a problem. What the developer should do is create a message, send the message to somewhere, and from there, done. Right? And is there other jobs, other developers' job to consume those messages, right? So I'm going to show you a thing. I hope and I also I'm going to show you some demos that I have prepared. So, hoping the internet works. I think it's very obvious the ease of using the thing. So, for example, with RabbitMQ, right? If we were to send the message, the bare-bone code that would be with their native SDK, it's good, but there are some things that we have to learn. Is that, for example, for this process order command message definition, so this is the class that gets sent over the network as a result of something. Okay, so process order, if we want to send this process order, we would serialize that, and then we would create some basic properties, and then we configure those properties, and then we had some headers, message type of that message. We confirm the selection, then we basic publish, we wait for confirmation, and if we want to consume, where we create an eventing basic consumer, and we do this eventing handling things that is not so easy to understand for a lot of new developers, at least. Then we do basic acknowledge, and then we basic consume. Huh? To send the message, all these? Why? It's like, I want to blah, 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 dot send, pass in the type, and that's it, not care about things, right? That would be the best scenario for me as a developer. With end service bus, we can do a similar thing, right? So we have the same processing message, and we do endpoint, send, we pass in, done, magic happens. Because we configured it like for the developer. How the processing stuff looks like? Well, we create a handler that implements iHandle messages. We give it the type that we care about, and then here is the actual business logic. All the knack, the back, the whatever, what's in there, no, I do not care about, right? And this makes it very easy for me whenever I want to switch the message brokers, because there are scenarios. I don't know, maybe we're now in Azure Service Bus and we get the better deal for Amazon, and we need to switch, right? Why invest like months in doing so when we could simply switch the transport and that's it? So for example, for Azure Service Bus, it's pretty close. It's still a lot of code to write, right? So you have the namespace, where is it, the transport type, if we want to use AMQP WebSockets. We create the endpoint, and it's the same thing in some cases. Process the messages async, then we serialize the body, we'll look at different things, we try to get a value, yada, yada. A lot of code, why? No, I just want to send my type and that's it, and do the same. Because the code looks the same, no matter the transport, right? We configure the connection string if needed, we set it as an environment variable, and that's it, right? So I shouldn't care about like technicalities, what's behind this. Nah, send message, this is the type, fill it with data, done, right? So let's see how a messaging scenario would look in code. So I hope the code is big enough for the last rows. So first I wanted to show you what happens, but I think it's pretty obvious. If you have API 1 calling API 2, right, HTTP request, because you have here some products and then you want to call to get the stocks for those products, if you only start the orders API and you create a new order, you'd be stuck waiting for stocks. And I'm gonna run this. So we're here. So when we create an order, yeah, we get an order model, we map it to a domain object, and then we call this HTTP client, hey, get stock, right? To see if there is available and I can continue with the order and save it. So if we do a request, we're here, but, well, something bad happens, I don't know. The stock API is down. We would get maybe this ugly stuff eventually. Sooner or later we get this, right? There is no connection, but we kind of lost the content of the request. So we lost money because we lost an order, right? We don't know what's there. But the first thing that we could do is to say, okay, yeah, this other service has issues, so how about wrapping some retrying policies around it? So I'm going to go here and install poly, maybe, because that's the most known. I'm going to say, hey, I want an HTTP retry strategy option with maximum retry attempts of 4. I'm going to delay 2 seconds between them and back off type exponential. And that's it. Cool. Solved my issues, right? And when you run again and do the same request, yes, it will retry by itself during the, according to the algorithm that I specified. But what happened if it's not successful, right? So do request. We're here. I'm going to remove the breakpoint. It will take longer this time, and we can see what's going on by looking at the console window. We see that we get an execution attempt to call that. So the retry policy is in place. Takes a while. Another attempt. We wait some more, and then another attempt, up until it reaches the retry limit, and some more. But in the end, we will get an exception, right? It's not like the retry policy would save somewhere in the database so we can retrieve it later. That's not possible, right? And yes, we did get a response with the same thing. The second API is not there. But how about we try to switch all these things to messaging? And you'll also have access to the source code, so don't worry, you'll get it at the end. For example, if we know what types of data we want to pass on, we would create a library called contracts, and this would be shared among the components that need to be shared. So for example, we have here events, a single event in this case, order created, which is nothing more than a regular C# class with some properties, right? And whoever wants to have access to this order created will get access to this contracts class library, so it's easier for us to distribute that. The idea is to keep everything clean, right? So no business logic, no other thing, just data storage. These events are super small, or as small as you need them. And the same would happen if we would have a command, right? So let's see how we can change this API to not call the stock this time, but pass in the information that we get from the calling party and to store it in the database. You'll note I'm using mass transit, so you'll have an example here. On the send endpoint, get the send endpoint. I know for a fact this is a point-to-point communication. We're passing in to this specific queue. We send whatever we receive, and we move on. And then we have a worker class that knows how to handle order creation. So when we start this, it will pick up messages from the queue and will do whatever the controller used to do and save it in the database. So it gets the order, maps it, I don't know, modifies it, whatever, and also can notify other components that, hey, an order has been created, okay? So let's run the orders controller again. The idea with these workers or consumers is to be as small as you can have them, so you can scale them independently, right? So if you have a component that knows how to create orders, that can be scaled as many times as you want it, because that's the only thing that it does, create orders. Okay, so now when I send an order again, I'm going to open RabbitMQ interface. And I'm going to look in the queues. And we're going to see a queue that is called create order command. And inside it, there is one message ready to be consumed, so it's not lost, right? So now when this is, of course, well, created, or we can get an accepted status code depending on the scenario. So if we want to fool the user in a way, hey, I got you, I'm going to contact you later, you get the 202 back, so accepted. Yeah, it's 2, it starts with 2, it's a success status code, but we don't give it anything back. And now, you see, there's nothing consuming that message that sits around in the queue. But if I want it to be consumed, I can go in here in the, where are you, messaging, order creation worker, and I can run the instance, but not before I add a breakpoint here. So right-click, debug. There are other ways of doing this, but it's easier during demos. And as soon as this is started, you'll notice that the broker pushes the message that is in the queue. So we can access the context, we can access the message property, which if we expand this, and I'm trying not to lose it, context.message is exactly the thing that got saved as a message from the order that was sent from Postman. So these are the properties. We get a status, a default status for that order, and so on, right? So it's there. We save it in the database, and we moved on. And also, we write this information as in the console window. Also, as a result of an order saving, we can publish, hey, an event, right? An order has been created. And what you'll see here is that nothing gets sent or created in the message broker. And that's because mass transit only creates queue as soon as you attach a consumer to it. Otherwise, it will appear as nothing happened, didn't work, right? So let's go ahead and start this notification worker that is interested in an event that happened in the system. So I'm going to do the same. So now I have two consumers that don't care about each other. They're attached to a queue inside the message queue, at the end of the queue. I'm going to finish this, and I'm going to do another request. OK. Let's see if this is working. Great. And another thing, I think the API is not running. Just let me check how many I have. Create order consumer and notification order created consumer and the API. So I can use Postman to create my orders. But this way, I can attach as many consumers I want, as many consumers can be interested in a specific event that happened, and I can react accordingly. So let's see. We save it. We publish the order. And now when we look in RabbitMQ, suddenly there is this order created notification. The naming can be controlled by you, or you can leave it to the chance by the default naming convention. Yeah, so if we look in here, we'll notice that the notification order received something, an order with an ID 14. And in here, there's a second message that was processed. I'm just writing something in here because I didn't auto-assign an ID just to mimic the things. OK, and another thing that I think I'm going to have enough time to show you is the request reply that can be done as over queues too. So we have an orders controller, and you'll see here when you download the code is that you have a get order that mimics how an HTTP response would look like. So it calls the client that listens on the messaging queues, and it will return back an order result if the order is found, or an order not found result if the order is not found. So I'm going to comment up the old code. This is traditional REST, not found and OK with that order. So when I run the API, I also have here a consumer attached. Hang on. What are you? Services. I'm gonna just verify order. I don't think I have a consumer created yet. You'll notice here that you have a request client just as you would have with HTTP. You register it in the pipeline and you will see it there. Request client. No, apparently I didn't implement the consumer yet. I was about to, but I'm going to push the code. Anyways, it will behave the same. The receiving part, the sender, the client, basically, the consumer of the API, will get OK or not found with an error message. So this can be mimicked. What would happen in the broker is another temporary queue with the default expiration time will be created every single time you do a request to that. So the response comes back through that error queue. OK, so what I'm going to do is to show you the recoverability part. I'm going to start a Docker instance with a tool that I think is very important to have. I have a question. Are you using messaging already? Awesome. With what? Azure Service Bus? ActiveMQ. Wrapper around it, like Mass Transit, Service Bus? Brighter? OK. It takes a while. So I tested it last night, and the images are pretty small, large. The internet is not that good, and it took a while. So some elevator music would have been nice. Can you help me with that? But some of the things are started, some of them are not. But in any case, if we want to talk more, you'll find me by the particular booths today. So I'm there if you have questions or curiosities. These are all green. So in theory, just in theory, practice, we know that sometimes doesn't work. So you'll notice a bunch of things. So you'll see bill error, bill order underscore error. Mass Transit does create a pair for our initial queue in case of an error. So that's the concept of a dead letter queue, pretty much. Creates a pair where we will store all the errors that happens in the system. So not lost, over there. But the idea is, as soon as your number of queues grows, it's kind of tedious to do the work. So what particular did was to create a showcase where this is public, so you will find it linked in my samples. So you run the scenario, and a bunch of orders for different funky fruits are sent. But some of those orders are not processed with success. So we see that an order with this order ID has mangosteen and whatever fruits are those failed. So the sales process failed, and of course the billing process failed. You'll see here what is the flow of messages pretty much. So client does an order, so the sales component gets in, publishes a message. That message is interesting for the billing component and for the shipping, right? So let's create an invoice or take the payment and also arrange the shipping. But as soon as we see errors, we can click here and see failures. And we'll see information about the errors happening in the system. And this is a thing that kind of is not available out of the box. You either implement it in your company, spending a lot of time, or you use this tool. So you get here all the failed messages. You'll see these grouped by the exception types or by the endpoint address, instance name, and so on. So everything is filtered in here. And you can inspect them individually. For example, the type of message that failed is order placed, happening in a specific endpoint. We can see the stack trace that happened. We can see the headers and the message body, of course. And one of the most important features is that you can edit and retry. So you figured out, hey, an error, an order ID is something is not correct, right? You can go in here and edit whatever you want to edit, and you click retry, and that message will be gone to the initial source that was supposed to process it. And this makes it very easy to deal with errors. Also, if you want, you can retry all, select them all and retry all, and why not? Delete them. It depends on how you want to treat your errors, gracefully or not so gracefully by deleting them, right? But this is a very important feature that we kind of do not have around the ecosystem. So give it a try. It's in the early access program, so tell us what you think about it. And as I told you, you can find me at the particular booth if you have questions. Key takeaway for today, use the wrapper on top of the infrastructure code because it will save you hours. So no matter the extraction, use it. Find one and use it, right? Either mass transit and service bus, Bright, or others that suit your purpose, use the abstraction because it's very useful. Okay, so keep in mind, HTTP is not the only option. You can find here a bit.ly that points to the repo with the code, and also the slides and the showcase with the recoverability thing that I showed you. And don't be shy, come by a particular booth and let's talk. Thank you for attending. I hope you learned something.